Hello everyone, welcome to this video. My name is Emerson Ahrari. I'm a Google Earth Engine expert. In this tutorial, I'm going to show you how to calculate percentile cover using Landsat data and regression technique. First of all, you must select your region of interest. This tutorial can be used for all around the world, no matter where is your region of interest. You can use this tutorial in a global scale as soon as the Landsat and MODIS data are available. So now, first of all, I'm gonna select a region in the north of Iran, including the tree cover. Here we have a region in the north of Iran. I'm gonna select a province here, as you can see here, and select it as a region of interest. So go to search places and dataset and call follow administrative layer border. As you can see, the follow administrative layer is available for all around the world based on 2015 update, and here the country boundary and first level province and also city level or second level is also available. I'm gonna select the province including tree cover for the region of interest. So import it to the code, and then through the map.add layer, I'm gonna show you the borders and also the different units or province units based on administrative layer border. Here you can see it, and also here is my region of interest. The simplest way to select your region of interest is mark it through a marker or marking tools available here. So make a new variable as a new region of interest. Variable equals to ROI. From input table, I'm gonna actually select those table or those features has coverage or overlapped with the geometry here. Then through the map.center objects, I'm gonna have focus on the region of interest, and then I'm gonna show the layer as a ROI here. If you run a code, after a few moments here, you can see the border of the target province. So in the next step, I'm gonna call percentile cover data that is available in the MODIS product. So now make another variable as MODIS equals to, go to search places and dataset and type MODIS continuous vegetation field or terra vegetation continuous field that is available early with 250 spatial resolution. Import it into the code as an image collection. Go to the data properties, and here you can see the data is available since 2000. If you go to the bands here, you will find the applicable bands available here. The one of them is percent tree cover. You can find the percent of vegetation, whether it is the tree or non-tree, using this product. That is very useful product for actually vegetation related studies and forest studies. So now I'm gonna actually calculate the percent tree cover using the Landsat data, but it is available in the MODIS format. Using regression technique, we can convert this product, or we can re-estimate percent tree cover using Landsat data based on regression relationship between Landsat NDVI and terra vegetation continuous field. First, let's copy the target band and then import it into the code as an image collection. Assign the image collection to the mode. Here we have an image collection, and then you can get a print to see for how many years the MODIS product or this product is available. We have 21 elements. If you go to the feature, you can see this product is available since 2000 until 2024 now. So, and if you go to the bands here, you can find out different bands available here. For example, the target band in this tutorial is percent tree cover. Let's copy and paste it. Through the dot select, you can select only the target band and run a code again. In the right panel, you will have a new image collection only included one target band, that is person tree cover, as you can see here. So if you go to the data properties, you can see if there is an escape factor for this product or not. Unfortunately, there is no scale value, and the values ranges from 0 to 100%. For example, a pixel with 50 means that 50% of this pixel covered by the tree cover. So now back to the code, and let's get a visual. Let's actually make a visual. Make a visualization for this product easily. So through the map.add layer, you can visualize the bands included in the modis. So now I'm gonna actually select one of them. For example, I'm gonna select the feature the tree cover percent for 2020. That's why you can make a filter date starting from 2020 and ends to 2021. So there it is. Let's make a print from using print mode. Just a moment. Print mode. In the right panel here, we have one image collection including one image. So now I'm gonna actually convert the image collection from collection format to a single image. So it is very easy to use that first because it is already included only one image. That's why that first help us to convert it from an image collection to an image format. In the right panel, now we have one image, and in the Google map here, you can see the vegetation cover in the forest and woods have higher values compared to the rest of the region. Here, as you can see, there are some pixels with a lighter and some pixels with a brighter value shows the higher percent of tree cover. Go to the inspector and select each pixel you want. For example, here we have a pixel shows 67, meaning that this pixel, 67% of this pixel covered by trees. Or if you go to the downstream here, only 18% of this pixel already covered by the trees. Yeah, this is actually a helpful technique to get understanding about the pixel values in these products. Now let's click this product based on a region of interest. Here, that click ROI, leave the visualization empty, and then here we can set a name for this product as a modis tree cover and use the false at the end. After a few moments, you will have a new layer as a modis tree cover. Because of the false here, you can see the output not visualized yet because we want to actually control visualization process through the false, and we want to show it whenever we want. That's highly speed up processing in the Google Earth Engine platform. Now if you click on the modis tree cover, here you can see the selected layer clipped based on the region of interest, and you can increase its contrast by 90% of values in this image. For example, the 90% of values in this image for the selected region starting from 7 and ends to 60, meaning that the lowest tree cover percent was 7% and the highest was 60%. If we consider only 90% of values, click on apply allows you to increase the contrast, as you can see here. This is the modis tree cover percentage that we have here, and now I'm gonna actually calculate the NDVI, the Landsat NDVI for this region that allows us to, then we want to actually find the relationship between a modest percent recover and Landsat NDVI to estimate these parameters for the Landsat data with higher spatial resolution. That's highly necessary for some of the studies to have higher spatial detail for such kind of products. So now I'm gonna make a new variable as LC8 Landsat collection 8 products equals to collections only including collection 1 and 2. Landsat LC means Landsat collection and 8 refers to the Landsat mission. That here I'm gonna use Landsat 8 data that is available since 2013, and this is the best Landsat collection that could be used alongside the modest product for 2020. Go to search places on dataset and type and look for Landsat 8 collection 2 level 2 data. Actually, the collection 2 level 2 is a kind of product already corrected atmospherically and radiometrically, and it is very helpful to use this product for spectral indices because already calculated and you don't need to apply or try for any atmospheric or radiometric correction. So I'm looking for Landsat 8 collection 2 level 2. Let's see how can I find it. It's a little tricky in the Earth engine because this product is TOA reflectance and the next one is actually real-time data. Now I'm trying to find Landsat collection 2 level 2. Yes, there it is, Landsat 8 collection 2 level 2 tier 1. So import it into the code, and now I'm gonna assign image collection, the second image collection to LC8, the second image collection called, and then we want to filter Landsat data based on a region of interest that is ROI and also the period of time that is 2020. So filter date including two variables, start and end. Start from 2020 and end to 2021, meaning that only 2020 images for 2020 selected in this case. And then filter bounds allows us to select the data or filter our data based on region of interest that is ROI, and you can see here. So now I want to actually calculate one average image for whole of 2020 for this region with NDVI value without cloud cover. It is better to define a filter regarding to the cloud cover. Let's first make a print to see how many Landsat data is available for this location, and 2020 141 elements is available. If you go to the data properties here, you can see a comprehensive metadata for Landsat images that allows you to filter your data based on different information. For example, one of the useful information is cloud cover over the land. I'm gonna use those of Landsat data in which cloud cover over the land is less than, for example, 10%, helps me to call those of cloud-free images for the further processing, because we want to have a clear image or clean image without any cloud impact for the regression relationship to avoid noises and biases comes from the cloud impact. So let's make a less than filter, that filter Earth engine, that filter gets less than. I'm gonna filter the images based on the land cover, images with cloud cover less than 10% considered for this region. So call the image and call the variable, and here only 51 element is available. and all of them have a cloud cover over the land less than 10%. There are two parameters here, cloud cover or cloud cover under land. Cloud cover meaning that some of the clouds may be covered by the covered the sea surface, and some of them covered the land only. As we don't want to work, we want to work only on the land area, and we want to keep the sea from our analysis. That's why the cloud cover is not matter, because we don't matter if the sea cover already covered by the clouds, only the land, and also cloud impact on the land is matter in this tutorial. So if you are working in a coastline region, it is very important to use the cloud cover over land instead of the cloud cover. But if you are working in actually, if your region surrounded by the land only, the cloud cover could be enough for the filtration process or cloud impact filtration. So now I'm gonna calculate the average of surface reflectance bands. If you go to the bands here, all the surface reflectance bands starting with S are underline B. And also this is the simplest pattern and way allows us to select the target band. All the bands starting with SRB and the rest is not matter. If you run a code again, you can see the surface reflectance bands already selected here. And the rest of them that we don't want to use them, remove. And here we can use the surface reflectance bands for the further analysis. So in the next step, I'm gonna calculate the average of surface reflectance values over 2020. The simplest way is to use the median technique to calculate the average. But the median in contrast to the average, the median avoid extreme high or extreme low values that may actually resulted from noises in the time series analysis. That's why when I'm working with satellite data or NDVI and surface reflectance values, prefer to use the median instead of the mean or average. So the average using median is calculated, and then we must actually apply the scale and factor already explained for the Landsat data. Here, if you go to the bands, the data characteristic for Landsat data, here you can see there are two values as a scale and offset that should be applied on each band separately. You must copy and paste it here through an equation. Here, make a new variable as LC8 corrected equals to get Landsat 8 data that is multiplied to the scale value and add to the offset value. Go to the data properties again, and this time copy the offset value. There is a linear relationship, and also this is a linear model allows you actually to convert your actually initial values in the Landsat product to surface reflectance range of values through the scale and offset. So now LC8 corrected, now the Landsat 8 surface reflectance score is better. SR is calculated. Let's get a print to make sure the surface reflectance values calculated here. In the right panel, now you will have one image with 7 bands, each one of them including the average reflectance value from images with less than cloud cover, from images with cloud cover less than 10% for 2020, and their values converted from initial range of values to a surface reflectance or a standard range. In the next step, we want to calculate the NDVI from this product. LC8 NDVI is another parameter here, equals to get LC8 surface reflectance data and calculate the normalized difference relationship between near infrared and the red region. The normalized difference is a kind of function calculates the normalization relationship between any band that you prefer. For example, here based on NDVI equation, we want to get normalization relationship between the near infrared band 5 and band red. This is the band 5 near infrared, and band red is band number 4. Rename it to NDVI just like that, and then throw the map.add layer. As you can see here, LC8 Landsat 8 NDVI could be visualized. So I want to actually clip this product based on a region of interest that's its border already defined through the ROI, and leave the visualization parameter empty, and here the layer name will be NDVI, and use the false at the end. Run a code again and remember to save it. So NDVI is a new layer already added here. If you click on NDVI, you can see the NDVI values for the region of interest. The normalized difference relationship, or NDVI, is the most popular vegetation index. Allows you to calculate, assess vegetation cover for your region of interest, and NDVI values ranges from -1 to +1. Higher values, higher vegetation cover, and lower values shows the higher vegetation cover in this product. You can also increase the contrast by different techniques or different tools available here. No matter if the contrast is low, because we want to use this product in the regression relationship, and the only thing is matter is the range of value that should be between -1 and +1 that it is already, and vegetation cover must actually reflected with the brighter color that it is in our images. So now we have NDVI and percent to recover in the MODIS products. Now we want to make a data set as training data. A new variable as training data created equals to the training data included the LC8 NDVI as a predictor in our model with MODIS percent recover or mod product here. Now let's get a print from training data to get more understanding about this variable. In the right panel, you will have one image including two bands, one of them NDVI and another one percent recover. Actually, the percent recover has integer structure, and this is the original product that we want to find its association with NDVI through a regression relationship. So the simplest way is to use the linear regression methods to assess their relationship, and also we can use the linear regression model to predict the percent recover from NDVI value. First of all, we want to find the relationship using the linear regression method. So now make a new variable as, for example, linear feet. Here, linear feet equals to bring training data. It is very important to have predictor first and original then. So then through that reduce region, you can calculate the linear model between these two variables. There are a couple of arguments for the reduce region. The first is a kind of reducer. Here, actually, I'm gonna use the linear fit model. As you can see, the linear fit returns computes the slope and offset for a linear regression of two inputs. We already have two inputs, and we want to get a slope and offset between that, explaining the changes and differences between these two variables. So the linear fit is the simplest linear regression in the Google Earth engine. So we want to get this relationship based on the region of interest. So geometry equals to the ROI, and spatial resolution for the Landsat data is 30 meter. Now, a linear fit model created. I'm gonna print to see what is inside this variable. So linear fit. Run a code, and here linear fit and is missed here. This is the linear fit. In the right panel, we have a dictionary returns an error about the too many pixels in this region. When the spatial resolution is very high for the extent regarding to the extent of your region, in this case you will face with errors such as too many pixels in this region. In that case, you can reduce the spatial resolution value, for example, from 30 to 100 meter. So run a code again. In the right panel, the dictionary, a new dictionary is under computing that will have a slope and offset explaining the differences between two inputs we already defined in this model. It may take a little bit longer in terms of processing, I mean, because here we have a big region, and also the spatial resolution is 100. If you want to have higher speed of processing, you must actually reduce the spatial resolution to 200 or 500 meter, that I don't suggest it. So here the offset and scale value estimated, these two values explaining the differences between inputs. Now we want to have the offset and scale as two different variables in the Earth engine environment. Let's make a new parameter as scale, for example, equals to from linear fit model, I'm gonna have the values first, and as we have two values here, the first is offset and the second will be scale. So, and another variable for offset equals to from linear fit get values first and then get the first value. So let's print the offset and scale value. Scale is equals to scale, and let's make a print for offset here. Offset. Run a code again. In the right panel, you will have a scale and offset here. As you can see, the offset now actually is a separate number. It is important to convert it from object to a number structure, because we want to use these values in the next computations. So Earth engine.number again must be used for the second variable. Save the variable and run it again. Here you will have the scale and offset values here, and now we can apply these values on NDVI image to actually estimate the percent cover or 3% cover for each pixel with 30 meter spatial resolution. Now I'm gonna make a new variable as LC8 underline. So here 3, for example, 3 equals to already NDVI calculated get LC8 NDVI, that is multiplied to the scale value and added to the offset value. The scale and offset, two variables explaining the relationship between initial NDVI and percent tree cover. So then I'm gonna actually rename this product to LC8 tree cover percentage or tree cover percent, whatever you want, and I'm gonna visualize the output as LC8 tree. So here it is. Let's save the code and then click the output based on the region of interest. Leave the visualization parameters empty, and the layer name is LC8 tree cover this time, and use the false at the end to avoid automatic visualization. Save the code and run it again. After a few moments, you will have a new layer as LC8 tree cover. Just click it on, and here you can see the land cover data. Sorry, the 3% cover or percent tree cover using Landsat 8, as you can see here. So you can increase the contrast using the 90% of values. Some of the pixels got negative values that might happen because of the water bodies or urban area. So click on apply here, and now we can make using the inspector, if you select on each pixel here, you can compare the values. For example, we already had 26 for the selected pixel, and now we estimated 24 for the Landsat data. If the data or the pixel values are too close, this is a good sign that shows we made a true model actually that is reliable for prediction. So this is the LC8 tree cover, meaning that these pixels in the Landsat image cover 14% of these pixel in the Landsat image covered by the vegetation tree cover, or in another pixel we have larger differences in the forest here. The original value was 52 and predicted value is around 42, and it is better to run the output to make it to make comparison easier for the user. Here, that if you use the run, and the output will show you. Now you can increase the contrast by 90% of values here. Go to the pixels and click, for example, 1 pixel. Now you can see, for example, the original was 51 and predicted value is 45. In the next system, I'm going to show you how to get rid of the non-vegetation pixels, such as the water and urban area first, and then we will go through the RMSE and calculate the differences between these two products. So now let's make another variable. Let's actually make a threshold to get rid of the the non-vegetation pixels. So as you know that all vegetation covers in the LC8 tree have values greater, including values greater than 0, meaning that the values less than 0 already all of them related to the non-vegetation covers, such as urban area and the water bodies. That's why we can make a threshold here from LC8 tree. Let's actually select pixels lower than 0. So now we will have a binary images including 0 and 1. 0 for actually non-vegetation, 0 for vegetation cover, 1 for actually the non-vegetation cover. So THR clicked based on region of interest, leave the visualization empty, here image threshold, and use the false at the end. Run a code again. Here you will have the layer values, the layer image that highlights the areas where we have negative values. that all of them equals to the water bodies and also non-urban non-vegetation covers. So now we can convert the white region to 0 values through the NOT. Here NOT allows us to reverse the function and give a value 1 to vegetation cover and gives value 0 to the non-vegetation cover. So if you run a code again, this time you can see the vegetation cover with the white color. After a few moments, all of the negative pixels showing with the dark pixels or actually dark regions. So now I can actually do the visualization here, or I can make a new layer as variable Landsat 8 LC8 tree cover equals to LC8 tree multiplied to THR. We can use the update mask here, but sometimes the update mask is a little actually heavy for the processing. If update mask didn't work well, you can multiply the Landsat 8 tree to the threshold image. Let's do the visualization now, and this time we want to visualize LC8 tree cover. So let's save the code and run it again. After a few moments, you will have a new LC8 tree cover. Hopefully all the negative value already removed, stretched to 90% of values, and this time the minimum is starting from 5 and the maximum is actually less than 100. So now you can see the contrast increased in the output, and now you can compare the Landsat tree cover with the MODIS tree cover. And the benefit of this method is helping us to have higher spatial detail for actually percent tree cover in our product. Here you can compare these two visually and quantitatively. So increase and also they compare them. As you can see clearly, we have higher spatial detail in the Landsat data that allows us to have a better understanding about the tree cover percent for our region of interest. Now in the next step, I'm going to show you how to calculate the RMSE between predicted tree cover and original or actual the tree cover already estimated with MODIS product and available here. To calculate the RMSE, first we must calculate the differences or subtraction between the original MODIS and LC8 tree cover. So now actually I'm doing subtraction first, and then the difference should reach to power 2 here, and now here we want to have difference that reach to the power here, get the difference image that power 2, so just like that, and then we want to calculate its average for the region of interest. The difference mean equals to difference power that reduce region, get the previous image through the reduced region and calculate its average for the region of interest, Earth engine that reducer that mean. As you can see here, and the scale value equals to 30 meter for the region of interest, but as we are working in a big region, it is better to set 100 for the scale value, and geometry equals to ROI. And now let's get a print to see if there is any problem in the code or not. In the right panel, go to switch to console, here a dictionary under computing. After a few moments, you can see the average value. This is 142, and just this is the average for whole of the region. if you want to see the root square for this value, we should actually calculate the SQRT. Here, first let's convert the object to a number through the values that get the first value, and then calculate the SQRT. And we must actually bring whole of the equation inside the number function. If you print now the output, the final value is the RMSE, or root mean square, that is around 12%. RMSE calculates the 12% actually differences between original value, and also between the original product and predicted product. So that's really helpful to understand how much actually difference do we have between predicted and original value. If you want to get export from the output at the end, here you can use exports.image.toDrive, because most of the users asking me how to get export from images. It is very important to have a successful export from the product. The image we want to get export is the Landsat 8 tree cover, including tree cover percent for tree cover percent values that is clipped based on the region of interest specifically, and the output name could be defined using description. Description is LC8 tree cover. You can set any other names you prefer, and the scale for the output should be 30 meter, and the region of interest equals to ROI, and the maximum pixel for the output, maximum pixels, equals to 1E13. And then the folder you want to get export, you want to save data in, could be, for example, test, or you can make any other folder. Just select a name for the folder, and then the folder automatically created in the Google Drive, and your output will be saved there. And CRS is another important argument here, actually explaining the coordinate system for the output, that typically we uses WGS84 using this code EPSG4326 here. So let's save the code and run it again. In the right panel, switch to task. After a few moments, you will have a new task for submission. So click on run and run it again. After a few moments, the process of saving started, and once the tab's color turned to blue, same as previous example, meaning that you can export, you can pick it up from the Google Drive. So and also this tutorial I used I used this tutorial, or I learned this tutorial from Google Earth Engine Cookbook. If you search on the net about Google Earth Engine book, here you will find it easily. Google Earth Engine book, already developed by the Earth Engine developers and freely accessible for all of the users. Here it is published by Springer, available here. You can find it easily here, and it is available in electronic format without any charge, and it is free of charge, available for all of the users. If you can easily download it without any issues, same as example I'm showing you here. And also I learned this topic and sharing with you from this book, and highly suggesting for the remote sensing users to study how to deal with Earth Engine using the materials available in this book. So now if you have any question or problem regarding to the code, you can reach me out on my YouTube channel, and the code example is available below the video in the description box on my YouTube channel. You can reach me out there and compare yours with mine, and if a problem still exists, you can reach me out on the comments then I will try to answer you as soon as possible. Thank you for your attention.